Okay, welcome back, Year 8, to our second screencast in this Pythagoras Theorem series. Now, before we get stuck into this lesson, we just want to do a little recap of what happened in part 1. Okay, so let's look at this. We had a look at right-angled triangles, didn't we? So here we are. There's a right-angled triangle. Now we labelled our sides A, B, and C. Now, what's the name of this, the longest side? He's got a special name because we need to refer to him quite a bit. That's right, it's the hypotenuse. Okay, so what we figured was through a series of some sort of graphical observations, and there are some fantastic algebraic proofs, etc. But right now, what we did the other day is enough, hopefully, for you to be happy and convinced that we have this relationship between the sides of a right-angled triangle such that c squared is equal to a squared plus b squared, right? So if you square the sides of a right-angled triangle, then the sum of the two shorter sides will equal the larger side, the hypotenuse. Right? And we looked at that, didn't we? We looked at constructing these squares on each of the sides, right down like this, and then we had a look at different ways of chopping up, chopping up B and placing it into C, and then joining A in. We saw that water wheel example, and like I said, there are some really nice algebraic proofs also, which you might be lucky enough to see later on in your mathematical lives. But for now, this guy here is what we're going to use, and it's a pretty powerful little relationship between these sides. So what we're going to do now is do some examples where, all right, have a look down here. We've got two sides of a right-angled triangle, and we need to find the third. And we're going to be concentrating in this section on just finding this hypotenuse, the longest side. So we're going to set this up, and I'll show you. We'll do a couple of examples. I'll get you to do some examples, so there'll be a bit of pause, do, play, and then I'll set you guys to work on your work requirements. So let's have a look at this example here. We've got a little triangle in front of us, right-angled importantly. We've got 6, 8, and C. We don't know what C is. We need to find C. So this is how I want you to set up each of your questions. So it'll write C squared equals 6 squared plus 8 squared, right? So in this case, we need to find out what C is. We go ahead and we work out what 6 squared is, and we figure out what 8 squared is, and we put those two guys together and we get 100. So that means that C squared, right, these three dots here, I don't know, maybe you haven't seen these guys before, they mean therefore. Big statement. Therefore, C squared equals 100. All right, just gives a nice flow from one line to the next. Right. So if C squared is 100, what is C equal to? Well, that's just one side of my. If I've got a square with an area of 100, then what's one side equal to? 100, whatever, meters squared, units squared. I've got what's one side? It's 10, isn't it? So that's what I want. I want C equals. I want the square root of 100. I want to know what multiplies by itself to get 100. All right, so that in this case is 10. Do we know what they are? It's not in any kind of units, is it? So it's just 10. C equals 10. All done. Okay, let's do the second example now. Maybe if you're feeling pretty confident, although this is a bit weird, this one, stick with me. All right, let's do it. C squared equals, what are my two shortest sides? 7 squared plus 9 squared. Okay, 7 squared, 49, thank you. 9 squared, 81, thank you. 49 plus 81, what is it? 130, I hear you say. C squared is 130. 130. Now, I know my square numbers. 1 squared, well, that's 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49, 8 squared is 64, 9 squared is 81. All right, stick with me. 10 squared is 100, 11 squared, what do we got? 121, 12 squared is hang on a sec, what's 130 then? This looks like it's not a square. I can't just get a whole number out of this. Righto, so therefore, C is equal to the square root of 130. Now this is a number that's not a whole number, right? It's more than 11 and it's less than 12. This type of number has a name. It's called a surd. All right, a surd is a square root of a number that can't be reduced to a whole number or an integer, right? So a surd, a little definition here of a surd. All right, it's the square root of a number that cannot be simplified to a whole number. So, all right, so put a little boundary around that. Okay, so that means that the square root of anything other than these numbers here. So the square root of 25, that's not a surd. Square root of 16, these are whole numbers. Square root of 9, no way. But square root of 2, square root of 3, square root of 4, no. Square root of 5, oh, that's a 5. Square root of 5, square root of 6, square root of 7, square root of 8, square root of 9, no. Square root of 10, these, all right, it goes on, these are all surds. They're part of this proud family of surds. Okay, you now know, perhaps, a new word. So we just leave it like that. Although we might get our calculators out. So what did it say? What did it say? Round the answer for part B to 2 decimal places. So into your, right, you've got to get a calculator out now. Look at this, I found a calculator. Right, so I'm going to find this is a pretty fancy calculator, but it doesn't really matter. I'm just showing you what you need to do. You need to find the square root button and punch in 130. Square root of 130, 11.4018, it says. 11.4018. So that is equal to 11.4018, but I need to round to 2, look at this, 2 decimal places. So I need to draw, 2 decimal places is here. So I'm going to write it as 11.40, is it 0? All right, so this 1 tells me to keep it at 0, doesn't it? All right, it tells me to keep it. If it was 5 or more, it would go up. So 11.40 is my answer. Right, here we go. Here is your PDP. Pause. PDF, I've written there. Pause, do, play. So go and do these two. I'll do them as well, and we'll come back and we'll compare our answers. All right, let's see how we've gone here. For question for part A, I found that we had 25. C squared was 25, so C was equal to 5. All right, so that's good. That's just a whole number, 5. Done. But over here in B, I get 3 squared plus 6 squared, which gives me 9 plus 36, which is 45. So just need a little bit of help with this because these are different, aren't they? So therefore, C is equal to the square root of 45. All right, now that is not a whole number because I know that 36 is 6 squared and then 49 is 7 squared. So it's somewhere between 6 and 7. On the number line, we would have 6 here and 7 here. Now that is the square root of 36, and that is the square root of 49. So in here somewhere is the square root of 45. All right, it's in between 6 and 7 somewhere. So we need to get our calculators out and find out what the square root of 45 is. So I'm going to go in, hit my square root button, punch in 45, hit enter. I've got 6.7082. 6.7, all right, 6.708. 6.7082. Again, I want it to 2 decimal places. So I'm drawing a line down here, and I'm deciding whether I want my 0 here, my second decimal digit, to stay at 0 or go up to 1. This here, this 8, this is my that's the one that determines the fate of the second decimal place, and the 8 suggests I better go up to 1. So 6.71 to 2dp is our result. Hopefully you went all right with that. Got one more example to do. Let's do this together. A rectangular wall is to be strengthened. So this is like a little applications question. You might see one of these a bit later in the exercise. Rectangular wall is to be strengthened by a diagonal brace. There it is. The wall is 6 meters wide, 3 meters high. Find the length of the brace required. Correct to the nearest centimeter. Here's Pythagoras in action. So, all right, really, this brace is a hypotenuse, isn't it? So I'm just going to call the brace C and say C squared equals 6 squared plus 3 squared, because really all I have here is a right-angled triangle that goes ding, ding, ding like this. All right, so let's find out the length of our brace to the nearest centimeter. 36 plus 9. Hang on a sec, this looks familiar. C squared equals 45. Therefore, C is equal to the square root of 45. Didn't we just do this? It was up here somewhere. 6 and 3, no different. So to the nearest centimeter, 6.7. I don't need to go to my calculator because I've already done it. What is 6.7 to the nearest centimeter? Is it closer to 7 or 6? It's closer to 7. So 7 centimeters. No, not centimeters. 7 meters to the nearest meter. Fantastic. Okay, we have put some questions together for you from exercise 4L. Go consult your work requirements and enjoy your Pythagoras. See you soon.